has dimension -1, so the product is dimensionless. Okay, so now we learned that the theory that we're looking at for can better be described as Yang-Mills, double copy Yang-Mills plus phi cubed theory. This has the right spectrum, it has the right 3-point amplitudes. Of course, there's many other 3-point amplitudes that you can check, but essentially these are the 3 important ones.
So you can also add 5 to the 4 and so forth. Like you write a hydrolytic coupling in gravity.
Yeah, so it's a good question whether you can add more scalar interactions. And so far I only analyzed 3-point amplitude, so we're actually completely ignoring higher point interaction between a scalar. And that's something I'm going to come back to. But I can give you the answer already, that we need to have phi 4 as well. But it doesn't come with an independent coupling constant, it's fixed in terms of gauge coupling constant.
But is that because you want to have minimal coupling in the gravity side, or I mean, if you change that, would you modify the gravity Lagrangian to something?
Well, I mean, so if you look at this theory, there's not much freedom. I mean, it's a gravity theory and a Yang-Mills theory, so they're pretty much fixed by symmetry.
No, I just meant you could have R squared, R to the fourth.
Oh, well, that's a good question. Yeah, that's not something I'm going to talk about. But it's a good question whether if you want to have modified gravity theories, whether you can also construct them.
No, I'm just suggesting that maybe adding the 5 to the 4 then generally would produce such terms in the gravity side.
Not in a naive way, but in some more intricate way, yeah, it can happen. Yeah.
Excuse me.
Yeah.
Is there a relation between two Yang-Mills?
Yeah.
Is there a relation between Yang-Mills and
This here?
Yeah.
Well, we know already that to get gravity theories, you basically need to take a product of 2 Yang-Mills series. But the numerators, I mean, it's a bit sketchy here, of course. But I mean, if the numerators has to be taken as a double copy between 2 Yang-Mills series, and that's how you get spin 2 particles interacting in a consistent way. Now you can modify one side in some way, and in particular adding phi cubed, adding scalars which interact with phi cubed, and that will give you such a different theory. Maybe you're wondering why I don't put phi cubed on the other side. Is that the question, or? Is there a relation? Oh no, sorry. No, it could be different Yang-Mills theories. It could be n equals 0, n equals 0, n equals 2, for example. Yeah, it could be different. Okay, so let me continue talking about just this gauge theory. So the goal here is to properly identify what this theory is. I mean, so far we only know its cubic interactions, and we need to know the full theory. So let me do it over here.
Sorry, how about the matching between symmetries and theories?
That's something I'm going to come back to in just a minute or so. Because right now I didn't say anything about the symmetries. So let's just try to just naively write up what it could be. So since we have vectors, and clearly the vectors just interact as the usual Yang-Mills, we assume that we're going to have f squared term. And some index here. And we also have scalars, so we assume that the scalars interact with the Yang-Mills field, and then they have to have covariant derivatives for the kinetic term. We also assume that the scalars are real because the Yang-Mills fields that they produce is real, so it's reasonable to expect that this is a real scale. And then we know that we have this term lambda phi cubed. Oh, let me use a different phi. We also know that there's an index, right? So there's more than one scalar, so we have to have an index. So we give it a bit more space. And presumably there is some coupling constant here, which we can parameterize as if A, B, C. We don't know anything about this object. And here's also index here. Now we know that this group index is not the gauge group. Because, as I said before, when we do the double copy, we simply drop the gauge group. There's no gauge group index here, so there's a gauge group index here which needs to be restored. So let's call it the gauge group index lowercase letters. And then, yeah, so here as well. So now, again, we have to somehow make this field indirect, and they're all in adjoint representation, so the only thing that's reasonable to write down is FABC, but this is just the usual structure constant for the gauge group. And now, we also, whenever we have an F, we have to have a coupling, so it's going to be a coupling there. Okay, so this is a pretty good guess for the theory that we're looking for. So we note here that there's this interesting structure. So let's say that we're talking about SUN groups. So we have SU, we have some SUN's color, and then we seem to have some SU and flavor, which are these capital letters. So now we need to so now how do we know that this is the correct theory? Well, we can continue computing higher point amplitudes and convince ourselves that it's correct. But computing higher point amplitudes in gravity is not always so easy. So is there some easier way to convince ourselves that this theory is the correct theory? Well, so we know that if a theory satisfies, well, if a theory if you can use the theory as in double copy construction, essentially what has to happen is that the theory satisfies color kinematics duality, which in turn means that there are a certain set of amplitude relations that theory has to satisfy. So, or correspondingly, we have to check whether this theory actually satisfies all the Jacobi relations for the numerators. So check if theory satisfies color kinematics duality. So if you do that, and if, for example, if you look at the 4-point amplitude, 4 scalars, and if you look at if you look at order lambda squared in this coupling here, then you will note that then you will only pick up terms corresponding to this term here. And then you will get a constraint on this coupling here. And it's not too hard to guess what that constraint is. The constraint is that this FABC has to obey the Jacobi relations. which just means that this object satisfies the same relations as this guy, so they're equal footing. Another thing you can note is that if you look at the same amplitude, but if you look at order g squared, so now you're only looking at terms which are on the first line. Then it doesn't work unless you add a phi 4 term. So here you can see that this theory does not satisfy. So this theory alone is, if you set the coupling lambda to 0 and just have this ordinary Yang-Mills theory with scalars, this theory does not satisfy color kinematic stability unless you add a phi 4 term. So let us do that. So the correct term is essentially this. So this is, it's going to be proportional to the gauge coupling because if you set this coupling to 0, that's the only coupling in the problem, so that has to be the one. And then it's just F, A, B, C, F. I don't know if you can read this, but I'm not sure if the details are so important. That's the first, well, let me write the scalars down here. G, A, C, A. So this term is just a standard term that you find in supersymmetric series, for example. It's a standard term that you find if you start from a higher dimensional Yang-Mills theory and dimensional reduce, you always land on this term. And now you can understand why that term is needed. Because if you start from this higher dimensional theory, and that's just going to be pure Yang-Mills, then you know that pure Yang-Mills is going to satisfy color kinematic stability, and therefore all dimensional reductions it's going to satisfy. Well, so that doesn't prove that you need it, but it's sort of give an indication that it might be a good thing to add that term. So now, now this is essentially complete because we cannot add more interaction. Yeah. This theory already satisfies polar kinematic stability, so there's no reason to add anything more. Okay, good.
So the first constraint will give the restriction on the number of scalars, right?
There is no restriction on the number of scalars. It just says that this has to be a structured constant of a Lie group. That's all it says. You're saying, well,
if the number, for example, is too small, then
oh yeah, so
that will mean
you have to have at least 3 scalars, of course, otherwise this F is 0. So it's totally antisymmetric. I mean, you can also imagine that if you say, if you imagine that this theory came from some string theory construction, then you can say, well, then there's a restriction because you started from 10-dimensional theory and then dimensional reduced. But it doesn't matter for this construction. It can be arbitrarily many scalars. It still works. And this works in any dimension, not just the usual dimensions. We checked all the correlations in dimensions 12 and higher, so it works. Now we convinced ourselves that this is a good theory to look at, but we still haven't convinced ourselves that this actually gives the right Yang-Mills-Einstein theory when you double copy it. So that's the claim. So I think I can erase this. So we want to claim that this is the right theory and then see what we can do to check it. And I'm just going to call it phi cubed, even though there's a phi 4 interaction. specify forward interaction is just constrained by the well, it's related to the gauge symmetry. So this is to be equal to gravity plus Yang-Mills. And I'm a bit, as I said previously, I'm glossing over this fact that there's also a dilaton axion contributing. It's not going to matter at the tree level, and for some amplitude loop level it's not going to matter. But in principle, if you also want to have the pure gravity Yang-Mills theory, you have to get rid of it. And this is known how to do it in principle, but this is not the topic of today's talk.
So Henrik, if I throw away the f squared, that's just give me the double copy for Yang-Mills, right? If I throw away the f squared.
F squared? You mean this piece?
No, the first
This?
term. Yeah, if I throw away that and I do double copy, that will give me
Oh
Yang-Mills.
yeah, that just gives Yang-Mills, yeah.
So wouldn't that be just an argument that if I just do double copy for Yang-Mills and then I add in the Yang-Mills piece and then I'm done?
Argument for what? Argument that this satisfies polykinetic
Yeah,
stability?
for why this will work.
Well, it's obvious that if you just have this piece, well, obvious from previous work, that if you just have this piece, it satisfies polykinetic stability. It's obvious if you have these two pieces that this also satisfies polykinetic stability because, or these three pieces, because there's just a dimensional reduction. It's obvious that this piece alone satisfies polykinetic stability
No,
because
but you need the last, those three pieces
Yeah.
to give the double copy for Yang-Mills, right?
yeah. So all of these three lines
Are necessary
or
for
three terms you need. But so you can easily convince yourself that individual pieces, works. I mean, not well, this pieces together, this piece alone, this piece alone. But the whole theory together is actually non-trivial at the satisfies polykinetic stability. And it's for any value of lambda. So this is it's an infinite family of theories.
any value of lambda just corresponds to the Yang-Mills coupling there.
Yeah. But you could imagine that there has to be some. In principle, it could have been that it works, but only if you tune the parameters the right way. But no, you don't have to tune the parameters. So this is, so we actually only checked that this works up to 6 points. So if somebody want to prove that this theory satisfies all the tree level amplitude relations to loop level, then go ahead, because that's not proven. Okay, so the claim is that this is the double copy we're looking for. So let's try to check that. So in the work, in the paper, basically that this talk is based on, maybe I should mention the authors of this paper. So it's Chiaroli. And Royman. So in this paper, we decided, well, we should check it in a slightly more interesting case than just the bosonic case. So we wanted to check it in some non-trivial gauge supergravity. So in particular, we looked at N equals 2 Yang-Mills-Einstein supergravity, and we looked in particular we looked in d equals 4 and d equals 5. And the reason why we looked in d equals 5 is because it's actually simpler d equals 5 than d equals 4. So in particular, the case we're going to look at is N equals 2 super Yang-Mills double copied with Yang-Mills plus phi cube. So this is this theory. Well, that's a claim. And here you might note that I added supersymmetry on this side, but not on the other side, and perhaps that's probably obvious to some people in this audience. But if you have this phi cube term, it's not very easy to make that supersymmetric. So assuming that there's no way to make it supersymmetric, this shows why this series can only have n equals 0, 1, 2, and 4 supersymmetries, as expected. Okay, so the first thing we should look at is that the spectrum works out. So let me just list the Yang-Mills spectrum, or the two copies, the spectrum with that, and then the gravity spectrum can then be worked out if anybody's interested. So n equals 2 has two fermions. It has a complex scalar, and so I'm going to write the on-shell components of the physical fields. So there's the plus helicity gluon, minus helicity gluons. There's two plus helicity fermions, two minus helicity fermions, and then there's the scalar and the complex conjugate, treating them as independent fields. And this is supposed to be tensored with just Yang-Mills and the scalar. No, I'm not gonna multiply it out, but I hope you're convinced if I say that this matches n equals 2 Yang-Mills-Einstein supergravity. So this will, in particular, this will have, well, let me first say, this will have the graviton, for example, which is this product. It will have gravitinos, which is this one times this one, and it will have vectors. It will have vectors on one hand from this product between the A and the phi here, and then between the phi and the A here. So, but it will also have dilaton and axion, so that's a cross term between the A's, so A plus and A minus. So, so now when we check that the spectrum worked, we want to check the 3-point amplitude. So the next step is to check 3-point. And then, in principle, we also want to go up to 4 points, and indeed, we did that in this paper. But I'm not going to bore you with actually showing the actual answers. Actually, the 3-point amplitudes are not that difficult. They're actually essentially what I already showed you, just generalize it to these fields. But in this paper, what we did is that we checked the spectrum, which is 2-point objects, I guess, and then we checked 3-point and 4-point. So we said, well, 2, 3, 4, infinity. So this is a physicist's proof that things work. Now you could say, well, why don't you check 5-point? Well, 5-point is too complicated because it's a very complicated supergravity theory. But just to give you a little bit flavor of what this theory is, the particular theory that we looked at, let me write down some facts about it. For example, the Lagrangian in 5 dimensions. So the 5-dimensional Lagrangian of this theory is actually a lot easier than the 4-dimensional one. Whoops. So we have this determinant of the field line again, and then we have, oops, yeah, okay, good. Then we have the Einstein-Hilbert term. I think I'm gonna drop, well, couplings are suppressed here. And then there's, again, we have the f mu nu squared. And there's, let me call now the labelings of the vectors I and j. And the principle, now since we have scalars in the theory, there's a non-trivial metric here. So let me call it a with a ring on top of it, ij. And there's more terms. There's scalars in this theory, so we have kinetic term for the scalar. So I'm just going to write down the abelian version of this theory, and then you have to imagine the non-abelian yourself. Oops, wrong scalar. So there's a number of scalars, so let me denote them by x and y. And this notation just follows the paper. This is a bit weird, maybe. The supergravity notation. So that's also a metric for the scalars. And then there is there's a term which does not depend on the metric, so I have to multiply by this factor again to get rid of it. So this only depends on the Civita term in 5 dimensions. And it's a 3-vector interaction. So that's the whole Lagrangian, the bosonic part of Lagrangian, sorry, for the non-abelian. So this is actually a rate stat. This is Maxwell. Okay.
Small aij is the coupling or
Small.
the
You
second
mean
terms?
second? What the?
Numerator in the second terms.
Oh, this.
Yeah.
Oh, this. So there's a. So yeah. So there's. Let me talk about the couplings here. So there's a function here, aij, and gxy, and thencijk. So the interesting fact about this 5-dimensional n equals 2 Yang-Mills theory is that, in fact, the only freedom that you have is in this term. This specifies the theory. So this comes back to this point that when you have n equals 2, the interactions are not specified, not unique to the spectrum. And this is encoded in this freedom here. So this CIGK tensor is free. But these other functions are not free, so that these are related. I don't know if I'm gonna bother. What time is it? How much time do we have? Half an hour. Okay. Yeah. So I can just write down, for an example. So yeah, let me just say some things why these functions are specified. So these functions are a function of the scalar. And that's what makes, well, that's one thing that makes gravity much more complicated than a gauge theory. Whereas these are just numbers. But to figure out these functions here, well, one has to do a lot of things. But in particular, one defines a pre-potential, which looks something like this. I'm going to drop some normalization factor here, but so the pre-potential is just contracting this with some auxiliary scalars.